So the water decreases until the water freezes. So first we have heat energy given out. And so heat energy to freeze the water from an unknown temperature to 0. So first, whatever the temperature of the water is, it will drop because it said till it freezes. So whatever the initial temperature is, the water will drop. The temperature of the water will drop till it reaches 0 because the freezing point of water is that. Then the temperature of ice form decreases. Okay, so the water temperature decreases until the water forms, the water freezes. Then the temperature of the ice falls. So after the temperature has been dropped to 0, then change of state will start. So plus energy for freezing. Then plus the ice form decreases until it becomes equal to that on the. So when the temperature, when the ice freezes, its temperature further falls from 0. Okay. Another latent heat energy from 0 to negative 60 degrees Celsius until it becomes equal to that on Mars. Okay, so this will be the stages, and we are told that the total energy to do that is equal to 210 kilojoules. So temperature, energy, okay, release in falling from an unknown temperature T to 0. MC, the change in temperature will be equal to the initial temperature minus 0, not the equilibrium, because it is dropping from whatever initial temperature it is to 0. So the unknown temperature minus 0 will be the change in temperature. Then latent heat of fusion, 0.4 times 33, a specific latent heat of fusion of ice. Then plus the heat energy given out by the substance to fall from, so 0.4 times specific heat capacity of ice, 2,200 times the change in temperature. Please note here that this is cooling. In cooling, the initial will be greater than the final. In heating, the final will be greater. In heating, because you are gaining, okay, this will lose, this will gain. So we expect the transfer to be final minus initial. But in cooling, the initial is always greater than the final, but change in temperature is always positive. So 0 minus 60. This we equate to 210 times 10 to the power 3. So this was the problem. This was the problem. The mistake we committed was that we were subtracting the, we were treating it as calorimetry, where heat gain is equal to heat loss. Okay. But in calorimetry, you must be given initial temperature, blah, blah, and all that to work that out. Amma?
Sir, please, I wanted to add that you said the freezing, the final temp will be greater than the initial temp, right?
Cooling.
Yes, in cooling.
Yes.
But sir, when it's being cooled, doesn't the temperature move to a negative number?
What I'm saying is that, you see, we had ice at a temperature of 0. Then its temperature further dropped from 0 to -60. Okay. And so if you compare 0 and -60, which one is greater?
0.
0. So we are treating the change in temperature to always be positive. So what we do is that we are not going to subtract, okay, negative 0 from -60, but rather -60 from the 0, because change in temperature, it must always be positive. Are you okay?
Okay.
So 0.4 times 4,200 T plus, when you multiply this, let's quickly go through the multiplication. Multiply this by this for me. Please, let's hurry up to start with what we have for the day.
1320.
Come again. Come again.
1320.
1320. Please, let's confirm. 0.4 times 3312. Okay, plus this side. 60 times 0.4 times 220.
5280.
5280 is equal to 1.
Yeah, 00.
52800.
Yes, please.
Okay. This is equal to 210 and 4083. So with this, whether you cancel the zeros or not, the value will be the same. I think this is 1680 plus, add this and this for us. 1320 plus 52,800. This is
5420.
come again.
54120.
Festus, your hand is up.
So please, the first, like when you're calculating for the first heat energy, why did you use the temperatures?
Why did I use temperature as what?
All the temperature T minus 0.
Okay, we don't know the temperature of the water on Earth. We don't know. So the initial temperature of the water on Earth is represented as T. Are you okay?
Okay.
So it's because we don't know, and that is what we are asked to calculate for. And so we represented that by the letter T. I hope that's fine.
Yes, sir.
Okay. So when you add everything, hey, this is 132, then 3 zeros, so then 5,400. Please check your calculations.
Yes, 10.
Let me
Because
check.
of the decimal.
Let's check the specific heat capacity. 3.0. Okay. 3.3 times 10 to the power 5. Okay, I misquoted it. So, this is 132,000. 132,000 plus, then we have 5,400. 5,400. When you total this and this, we have 18,2400. 18,2400. Good.
Stage, yeah.
Hello.
This the 5400. Please, isn't it 52800?
Multiply 0.4 by 3.3 times 10 to the power 5. Hurry up, let's confirm. 0.4 times
Mr.
3.3.
Dia.
Hello.
Mr. Dia, is that not what is giving the 132000?
This is giving us this. Then confirm the 0.4 times 2200 times 60.
Mr. Dia is 52800.
52800. Okay, then add this and this.
184800.
184800. 210123. Okay. Yeah. Then quickly help me determine the value of.
Mr. Dia,
Hello.
please, where from the 2200?
That's a specific heat capacity of ice. That's the specific heat capacity of ice. MC delta T.
But you give us 21 and 210.
No, the 210 kilojoules is the heat energy that is lost. Okay.
Okay, but still give us 2100.
It is that they gave us 2,100.
Yes, please.
Oh, okay. I'm carrying old values. Okay. Actually, this is the that's of ice, but questions when it comes to questions, they have their own values, so we must always work with whatever is given.
Okay, and then so the 52,000 will be 52,400.
So just give me this. Just calculate this and this for me. This plus this.
182,400.
182,400. Okay.
Yes.
All right. So 1680 T is equal to 210 minus 182,400. And the rest T will be equal to
164.3.
come again.
164.3 degrees Celsius.
164.3 degrees Celsius.
Yes.
So the rest, please go through the multiplication. What is important is the method. Okay. What is important is the method. Let's continue with whatever we're doing. Please, do you have any question on this? All right, then let's continue with our wave motion. So we started with whatever wave motion is. And a wave motion is a traveling disturbance that carry energy from one point of a medium to another point. And the source of every wave is vibration of the particles. The source of every wave is the vibration of the particles. Meaning the initial particles must vibrate when affected by a certain source of energy. Okay, so there must be a source of energy to hit the particles and the energy will be transferred from particle to particle, on and on and on, so it dies out at the shore. Okay, so waves are a traveling disturbance from one particle to another particle, from another particle, on and on and on. But this traveling disturbance is as a result of energy being transferred from one point to other point indefinitely. The source of every wave is the vibration of particles. So when particles vibrate, it starts waves. Okay. Now we also realize that in formation of waves transfer energy. Waves transfer energy, but not matter. Hence, the saying that the sea never gets flooded, because what is coming there is actually energy that is passing through the water medium. But as the energy moves on, it shakes the medium. And so you see it as if something is being pushed. But it isn't actually something that is being pushed, but the energy transferred vibrates the medium. So the medium, the particles of the medium are in constant up and down or to and fro motion. The reason why we picture it as if there is something, the water seems to be moving in the case of ocean wave. Okay, so waves transfer energy but not matter. Now let's discuss types of waves. Types of waves. We find ourselves in an ocean of wave, meaning wave, what we term as wave is all around us, and we are always swimming in waves, because we have, apart from mechanical waves, we have a lot of electromagnetic waves. We use television. Television signal can be is received through waves. We use mobile phone. Okay, the mobile cellular phones, which you operate on principle of waves. We have DSTV. We have multi-TV. Okay, aeroplanes. Okay, moving in our earth space. Okay, communicate using radio. So we actually find ourselves then, so long as we have this telecommunication masts, poles within our community, they always also communicate through waves. So we find ourselves in an ocean of waves. That is why they say that if you have a mobile phone in your pockets, okay, be very careful, because you can be harmed, blah, 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 and all that. Waves is all around us. So types of waves, we can discuss ocean wave. Ocean wave, then the wave from during tides, tidal waves. We have water wave. Ripples on the surface of water. We have sound wave. We have wave on a rope. Wave on a rope. Then we also have electromagnetic waves. electromagnetic waves, which we can actually break down to gamma rays, S-ray, gamma ray, S-ray, ultraviolet, UV, radiation. We have infrared. We have visible light. These are all electromagnetic waves. Visible light, we can also talk about microwaves, microwave for long distance communication, TV signals, then other waves as well. Okay, so these are different types of waves. And if we even have some other examples as well. So when we are to talk about the various different types of waves, these are a tall list of, I've even forgotten another one. We also have seismic wave. That is earthquake wave. Seismic or earthquake wave. And I'm bringing it down here for a reason. Okay, so for types of waves, we have a tall list and even other examples you can find in books. Now, this tall list of waves are classified. We are going to classify them, okay, similar to what the biologists, the taxonomists does by classifying organisms based on certain observable features they have. Okay, so we are going to classify these waves based on the fact that when the wave is propagated from one point to another point, will it require medium similar to human beings? If I'm to move from one area, town, to another town, in my mode of movement, will I require a vehicle, or I can just move through the air and go? Okay, so under this classification, we put waves under two main umbrellas. That is mechanical waves and electromagnetic waves. Electromagnetic, shortened as EM waves. EM waves. So the mechanical waves, the electromagnetic waves are not types. They are classification. We are classifying these examples under these two main headings. Now, what is mechanical waves? Mechanical waves are all these examples of waves that, when propagated, would require a medium before they are propagated from one point to another. A typical example is that, do you know when you go to space, they say, I've not been there before, so they say that in space, because there is no air, when you speak using your vocal cord, nobody hears you. So when astronauts go to space, they communicate with gadgets that is designed for that purpose. Because if without that gadget. When you go there, nobody hears you. Lizzie, nobody hears you. Okay. And this is because there is no air. In physics, we have this experiment where when you have a vessel and the air is siphoned out of the vessel, and then electric bell is pushed into the vessel, and then the circuit is closed to ring. Because the air is siphoned out of the bottle, the gong of the bell will be clapping, but nobody hears the sound produced from it. Meaning that in the absence of air, sound waves cannot move, cannot be propagated. Okay, so when we talk about mechanical waves are waves that require a medium for their propagation. Okay, so under this tall list, ocean wave. There is no ocean wave if there is no ocean. Where will be the ocean wave itself if there is no ocean? So under this classification, we'll put here ocean wave. Clearly, tidal wave will also be here. Then water wave would also be under this classification. What will be wave on a rope if there is no rope? Okay, so wave on a rope will be here. Then we'll also put here sound wave, because if there is no air, sound cannot be propagated. Then we'll also put under this classification earthquake, seismic wave. Seismic, because if there is no air, where will be earthquake? Then the quake will rather tend to slow. So seismic wave. So these are waves that is being classified under mechanical waves. So mechanical waves require a medium for propagation. Then electromagnetic. This kind of wave is termed electromagnetic because they exhibit both electrical and magnetic property. Hence, the name electro and magnetic. They exhibit electrical property as well as magnetic property. Now, electromagnetic waves are waves that does not require a medium. In fact, these waves are such that when there is a medium, it can be propagated. When there is no medium, it can also be propagated. So they do not require any medium for propagation. Let me give you a practical situation. You see, the sun, the light from the sun, okay, passes through the various spheres, okay, stratosphere, strobosphere, and all the spheres, even ionosphere, stratosphere, strobosphere, then comes to atmosphere where there is air. In those spheres, okay, some of them there is no air, yet the light, visible light from the sun could still move through and then come to the atmosphere where there is air for us to receive it. So clearly it tells you that the visible light from the sun can still be propagated through area which is devoid of air molecules. Another classification is that for long distance communication, before before, if you want to call somebody in abroad, in Ghana, your call would go to the communication stations, the communication the telcos. They are mass, the pole within our community. It will be picked on and on and on and is sent to Accra, their main transmission office. Then the gateway satellite in Ghana is at Kuntunsi, around Pokuasi area. So all calls moving out of Ghana will be given to that satellite. Then the satellite is directed to space. So the satellite in Kuntunsi communicates to another satellite, okay, in space. So all outside calls will be given to the space, the satellite in space. In space, there is no air molecules, yet the electromagnetic waves from the main satellite in Ghana can send it to another satellite. Then it will be given to a main transmission office in US before US looks for the destination of the call. So in this particular situation, electromagnetic waves is moving from Ghana to space. In space, there's no air molecules, yet it could reach there and then be sent to its destination. Okay, so these are two classical examples of how these waves does not depend on a medium. The same electromagnetic waves, okay, can also be sent through copper wires. Look at the telephones we use in our homes, the landline. What feeds it, causes the ringing and all that is still electromagnetic waves. So these are the kind of waves, okay, that actually does not depend on medium. When there's a medium, fine, it can work. When there's no medium, it can still work. And we term this as electromagnetic waves. So all the examples listed from gamma ray down to radio waves, TV signals, radio waves. Let me include radio waves. Radio waves comes under electromagnetic wave. Okay. From gamma down to radio waves comes under electromagnetic wave. And all of them have special properties. And the special property they have is that they could all be transmitted at a speed of 3 times 10 to the power 8 meter per second. So all the electromagnetic waves travel at a speed of this. All the electromagnetic waves do not require a medium before propagated. Please, any question from Amma? Yeah, Amma. Charlotte, get ready. Amma, let's. Hello.
Please, you gave a reason why the gamma rays, X-rays, etc. fall under electromagnetic waves. Did you give a reason why number 1, 2?
I said that all the electromagnetic waves here travel at a speed of 300 million meter per second. Okay. And 2, all the electromagnetic waves do not require a medium before propagated. So gamma ray, X-ray also have those key properties.
So said the number 1 to 5. Why did they find a mechanical wave? Which reason did you give?
Because they will require a medium before they can be sent from one point to another. As I speak to you, if there is no air, it cannot be. You can't even hear me from your home.
Okay.
All right. Another hand is up. Please go ahead. Tab, go ahead. Ask your question. Oh, Tab, I'm waiting for you. Okay, maybe it's a mistake. All right. So that's it. Then under the same tall list of waves, there is also another classification. So please, we are classifying the types of waves based on the fact that it requires a medium for propagation or does not. There is another classification of the same tall list, and that classification is waves can be classified as transverse and longitudinal. Waves can also be classified as transverse and longitudinal. So let's look at what goes into this classification. So we are classifying the types of waves under transverse and longitudinal. Longitudinal.
Mr. Elia, please, is that also another classification?
Yes, that's also another classification. We are classifying these same waves. Okay. Now, under this classification, you see, under the first classification, we are looking at whether the waves would require a medium for propagation or not. Now, under this classification, we are looking at how the wave itself is formed. We know that before a wave is formed, it's as a result of vibration of the particles affected by energy. So energy from external must hit the particles, and the particles vibrate to form the energy, the wave. So as the particles vibrate, it means that the energy received is transmitted from one particle to another particle, on and on and on. Okay, so we are looking at when the energy hits the particles, in what form do the particles vibrate, and how is the energy transmitted? So it's like a Amma, Charlotte, Lizzie, Stephanie, Tucci, you are the particles. How are you vibrating? You are affected by the first person. Ekweadoma receive the energy. The energy will cause Ekweadoma to vibrate. As Ekweadoma vibrates, Charlotte will also be vibrating. Lizzie, Stephanie, Tucci, Calvin, on and on and on. But the question is that, how are they vibrating? How are the particles? They vibrate with a certain style. So how are they vibrating? And as they vibrate, how is the energy transmitted from the vibrating particles? The transmission of the energy is what we are calling as a wave. Okay, so under this kind of classification, transverse wave, here, the style of vibration of the particles is that the particles vibrate up and down. So particle Aquia, particle Charlotte, particle Lizzie, Stephanie, particle Calvin, Tucci vibrate in this manner, up and down. So up, down, all of you. And as they vibrate up and down, the energy that is being transmitted through the particles is transmitted perpendicular to the vibration of the particle. So As the particle vibrates in this manner, up and down form or manner, then the energy is also transmitted this way. So yours is to vibrate, move up and down like this, and the energy is sent perpendicular to your style of vibration. So in a transverse wave, the vibration of the particles of the medium is perpendicular to the propagation of the wave, or is perpendicular to the transmission of the energy through the particles. That is what we mean by transverse wave.
Please, can you come again with that part?
I'll write it for you.
Okay.
So in a transverse wave, the vibration of the particles of the medium is perpendicular to the propagation of the wave. So under transverse wave, we have this as the up and down vibration, up and down vibration of the particles, and we have this as the propagation of wave, and vibration, the up and vibration of particles is always perpendicular to the propagation of the wave. This is the meaning of this classification termed as transverse wave. So again, transverse wave, it isn't an example, a kind of wave, but it's transverse wave, longitudinal wave is classification of these waves based on how the particles vibrate and how the wave is being formed. So as the particles vibrate in this manner, the wave formed is also like this. And then it goes in this direction. And all electromagnetic waves fall under this classification. So all electromagnetic waves, starting from gamma ray down to radio waves, are transverse wave. Apart from electromagnetic wave, wave on a rope is also transverse. Okay. Water wave is also transverse. However, ocean wave, tidal wave is mixed. I'll talk about that. It's mixed. I'll explain what we mean by, or what I mean by mixed. Okay. But all EM waves, wave on a rope, water wave are all transverse waves. Then we have the other classification, which is longitudinal wave. Longitudinal. longitudinal waves. Under this classification, in the two classification, we are looking at the style of vibration of the particles, and then how the energy, as the particles vibrate, how is the energy transmitted, or the wave is, how is the wave formed? Okay. Under this classification, particle Equiadoma, particle Charlotte, Kelvin, Tucci, Doku, Lizzie, Samuela. This time before, you particles were vibrating up and down. This time it's back and forth vibration. So this time you vibrate like this. Okay, back, forth, in this manner. So as particles vibrate back and forth in this way, then the energy is also transmitted parallel to the vibration of the particles. So vibration of particles and propagation of wave. So we say that in a longitudinal wave, the vibration of particles is parallel to the propagation of the wave. So in a longitudinal wave, the vibration of particles is parallel to the propagation of wave. Okay. And sound wave, example of wave, example, sound wave. Sound wave is an example of or falls under this classification. Now I was talking about ocean and tidal wave. For ocean and tidal wave, and even deep water wave, the wave formed on the surface, the shallow parts of the water, ocean, tides, and then the surface is transverse in nature. But in deep waters, okay, the surface, I said the surface wave is transverse in nature. But the deeper side, within the deeper side of it, the wave formed in the deeper side of the ocean is longitudinal. That is why I earlier said that these are mixed, both transverse and longitudinal. So on the surface, transverse waves are formed, whereas at the depth of it, longitudinal waves are formed for ocean, tidal, and then even water. But this water wave we are talking about is having water in a bowl and then dropping a stone or pebble into it. But we are also talking about a whole river, the ocean, the wave formed on the surface, and then at the deeper side of rivers and all that. So it's a mixed kind of yes. Please, any question? All right. Then let's look at wave profile. How do we simulate wave? How is it? What and what? How do I picture it? If I'm to picture what a wave is or draw, how will that be done? We've seen characteristics, how it is formed, types, but the wave profile. The wave profile. A wave,
Mr.
Ama,
Please, isn't the tidal wave the same as the ocean wave?
no, we have the tides. The tides, how the tides are is formed is different from the wave you see on the surface of the ocean. Okay.
Alright.
The tide is different from the everyday wave you see on the surface of the ocean. The wave you see on the surface of the ocean is as a result of the strong wind, okay, at the inner part of the sea, which blows, and then the energy of the wind transferred to the water molecules, and then propagated on and on and on till it dies out at the seashore. But the tides are formed due to the gravitational pull of the earth. Okay, so they are not the same. How they are formed isn't the same thing.
Okay.
So that is why if you are somebody who regularly visits the ocean, when you go to the beach early in the morning, it's always as if the sea seems to overflow its banks. It occurs in the morning, it occurs in the evening. These observations are actually due to the tides. But the everyday logologic thing, that macaroni-like thing you see on the surface of the ocean is a wave. The ocean wave. Okay, so the wave profile. We draw X and Y axis. A wave is actually a simple harmonic kind of motion. That repeated kind of motion. When the surface of the ocean is not disturbed by any external energy, the water is undisturbed, just quiet. When it is quiet, we use the horizontal axis to represent the equilibrium position of the wave or of the water, the undisturbed nature of the. Now, when the surface of the water is hit by external energy, the water molecules begin to vibrate. So, their regular vibration, the up and down vibration, will be indicated by the vertical axis, the Y. So, Y, X. X representing the equilibrium position of the particles of the medium undisturbed. So, if the medium is not disturbed, its surface looks like this. Now, when it is disturbed, particles vibrate in that up and down manner, transverse. So there's a point where the particle seems to vibrate a little, so much so much maximum vibration. Then some of them would also vibrate. Okay, so this point represents the extent of displacement of the particle from the equilibrium position. Okay, but look at me as a wave. When I'm not disturbed, I'm quiet. When I'm disturbed, I move like this. Okay, so that's what is happening. So this point indicated as dots represents the vibration of the particles above the equilibrium position. So over here, some particles are vibrating small. Some of them are also vibrating so much. And this is the maximum particle vibration over here. Okay, so the dots indicated represent particle vibration. When a particle is here, it means it has not vibrated. Okay, then because it's an up and down thing, we also have the same thing happening here. Because, as I said, it's an up and down thing. Okay, and this thing repeatedly, like, so we picture a wave as a simple harmonic function, and every simple harmonic function is a repeated function. That is why we picture a wave as this. This shape is a sine, curve, and so we say that a wave is sinusoidal. Sinusoidal, meaning a wave has a sine shape or function. A sine function is like this. A sine function is like what I've drawn. It can also be a cosine function. So that SHM, a sine function starts from 0, whereas a cosine function starts from this. So a wave can also be drawn as this or this. Okay. So because a wave is a harmonic function, it is denoted or drawn to have the shape of a sine or cosine function. Any question? Charlotte, any question?
No, please.
Amma, Kelvin. All right.
No.
So let's take a trip, excursion into the wave and look at the parts. Okay. On the outside, this is how a wave looks like. Let's take a trip into the life of the wave. We are coming to embark on excursion into the inner parts of the wave. And here we'll do this discussion using a transverse wave, where particles vibrate perpendicularly up and down manner, and then the wave is formed perpendicularly to it. Simple harmonic motion. This is the Y represents the displacement of the wave. Displacement Y. the maximum displacement. So there is a point of, I said, what you see indicates vibration of particles from the equilibrium position. A point of maximum particle vibration, if we consider 1, 2, 3, 4, 5, and 6, we realize that the 6th point is the point where particles have been displaced or vibrated so much, or vibrate so much. This point of maximum particle vibration is termed as the crest. So the crest is a maximum particle vibration. There are so many particles vibrating, but the maximum one upwardly is known as a crest. So the crest is the maximum particle vibration. Okay. Maximum positive particle vibration. Positive because we indicate this part as positive, the down part as negative. So the crest is always at the positive end. So along the line, you find crest here, crest. Then we have Mr. being a particle is vibrating. I'm going up and down. When I move down, my maximum vibration downwards, my maximum downward vibration also has a name. My maximum upward vibration has a name as a crest. My maximum downward vibration is also known as the crest. The up one seems to be shorter. So maximum downward particle vibration would occur here, because particles, and the one vibrating so much, if we measure, and it's known as trough. So the trough is a maximum downward vibration of particles. The crest is maximum upward vibration of particles. Maximum downward vibration of particles is the trough. And simple harmonic wave must have the same amplitude. So there's always, whatever is here should be. So we have trough here, trough here. Then for free oscillation, when we consider the amplitude of the wave, the maximum displacement of the whole wave itself, whether up or down, this point measured from the y-axis, from where crest is termed as the amplitude of the wave. So this is the amplitude, A. Amplitude, another same amplitude, measured from X to where trough is. So we define amplitude as the maximum displacement of a wave. The amplitude is the maximum displacement of a wave. The crest is the maximum upward vibration of particles. Class, please let me take a short of attendance. Okay, up to where we've gotten to. So the amplitude is the maximum vibration, the maximum displacement of the wave, the whole wave. And we are considering this to be a free oscillation, okay, where the amplitude of the wave is the same, even though practically waves do not exist like that. Then, so we've noticed the crest and trough, then amplitude of the wave. Then let's identify what we mean by wavelength. The wavelength of a wave, what we call as full wave. Then we'll also look at the frequency, period, then velocity or speed of a wave. Basically, we are looking at the measurable properties of a wave. So the displacement of the wave, the displacement. This is displacement y1. A displacement y2 here is greater than y1. This is the maximum displacement where of a vibrating particle, where the amplitude is measured from. So the displacement of a wave or the medium is the distance moved by the particles within the medium from their equilibrium position. Okay, the distance moved by the particles within the medium from their equilibrium or mean position. And the displacement is measured in the SI unit of displacement is meters. Then the amplitude of oscillation of the whole wave is the maximum displacement of the particles from the equilibrium position. The SI unit is also in meters. So when you locate crest or trough, you can easily calculate for the amplitude. Wavelength. We define a wavelength as the distance wavelength is actually the distance between 2 points that are in phase. Some other books will define wavelength as the distance between two successive crests or troughs. Distance between two successive crests or troughs. Now let's try to understand wavelength by the first definition, and you will later understand why this second definition of wavelength also comes in. So wavelength is the distance between two successive 2 points that are in phase. Let's look at what we mean by points that are in phase. Now, when points are said to be in phase, they occur at the same angle, and the points also vibrate together. So, points in phase occur at the same angle and also vibrate together. Vibrating together, we won't talk about it because from two-dimensional drawing, we can see points that are vibrating. But we can depict points that occur at the same angle. So this is a simple harmonic wave. A complete oscillation is equal to an angle of 360 degrees or 2 pi radian. So this is equal to an angle of 360 degrees or 2 pi. This point is also equal to an angle of 180 degrees or plus or
Pi.
pi. This is an angle of 90 degrees or
Pi on 2.
pi on 2. This is an angle of 270 or hey, you've forgotten your simple harmonic motion.
3 pi on 2.
3 pi on 2. I have a point O, A, B, C, D, E, F. This is 360 plus 90. $420 or this is another 90. So 510. Correct? Let me draw a last point.
Mr.
Hello.
Please, 360 plus 90, is it 420?
Add it for me. I'm waiting for you.
Mr. That is 450 rather.
You won't talk. You won't talk. Give me the radian equivalent. Equia. What is the radian equivalent of 450?
5 on 2 pi.
Pi on 2.
Come again. Come again.
5 pi on 2.
Plus 90.
540.
The radian equivalent.
3 pi.
Sana medebe mumu. Uh-huh. Is it 510? Charlotte, is it 510?
Please, which one?
This point. F, J, H. What is this angle in degree? Then in radian, give it.
630.
30.
Radian. Meaning we can express
7 on 2 pi.
7 on 2 pi. Meaning we can express the angle both in degree or in radian. And that's exactly what I'm doing. Now, we are saying that a wavelength the distance between 2 points that are in phase in phase. Please check the spelling, not your own phase. No. In phase. When points are in phase, they occur at the same angle. So let's notice the points that occur at the same angle. This is 0. This is 0. This point is 360. Do you know that the location of the angle 0 degrees is equivalent to 360?
Yes.
This is because when you draw a circle, divide it into quadrants. This is 0, 90, 180, 270, back to 360. So 0 and 360 occur at the same point. So it means the points O, and E occur at the same angle, and so we say they are in phase. This is 90. This is 360 plus 90. So 90 degrees and 450 occur at the same angle. Once this is 360, which is the ending and the beginning of this full wave, meaning this point angle is the same as 90. So the points A and F occur at the same angle, and so they are also in phase. Then point B. What is the counterpart of the point B?
G.
So B and G, 180 are also in phase. When we look at it from the downwards point of view, this is the angle to 270, and it will match with this point 2. So points D and H are also in phase. Amma,
Mr. Adria, please. See why you've written the D. Isn't it the same for the C?
oh no, we are. Oh yes. I didn't realize it. So either C or D. So the points D and H are in phase. They occur at the same angle. Okay. So when we talk about wavelength of a wave, it's basically the distance between 2 points that is in phase. And when points are in phase, they occur at the same angle. Okay. And so because of this, we can say that one full wave, which is wavelength, can be O to E. This is wavelength lambda. Wavelength can also be from crest, successive or consecutive crest. The distance between two successive crests. Because A and F are in phase. Wavelength can also be the distance between two successive troughs from D to H. This distance is also a wavelength. The reason for the definition that a wavelength is the distance between two successive crests or troughs. This is because two successive crests or troughs are in phase. Or simply, a wavelength is the distance between 2 points that are in phase. Any question? And the SI unit for wavelength is a length. So still in meter, SI units. All right. Then frequency. So if I ask you to calculate a wavelength, anyway, we will apply this in solving problems so you understand. Frequency. What is frequency in simple harmonic motion? SHM. Can somebody help us? Frequency in simple harmonic motion. Charlotte,
Yes, please.
what is frequency in simple harmonic motion or in circular motion? Oh, Charlotte, you've forgotten. Ekwe you think you can be quiet. Ekwe what is frequency?
Miss Dedia.
Charlotte.
I don't know if what I remember is the right thing.
Oh, just try.
Okay.
We are learning.
The number of oscillation that the particle will perform per time.
Okay, that is Charlotte's view, which is not totally wrong, but Charlotte will get 3 out of 5.
Oh,
Okay, Natalie. Natalie, it's been a while. Speak. Natalie, are you there? Hey, all right. Festus, what is frequency? Any frequency you can remember from any other topic.
So,
Mhm.
the number of complete oscillations that a particle makes per unit time.
You are not wrong. Okay, so both answers not wrong. So when we talk about frequency, we are talking about the number of complete oscillations or cycles, okay, a wave makes or made within a given time. But often for frequency, we peg it to 1 second. So number of complete cycles or waves made within a second. Okay. So frequency of oscillation is the number of complete oscillations or cycles a wave makes in 1 second. So it is actually within a given time, but we are narrowing it down to a specific time, which is 1 second. So frequency F is equal to number of waves or cycles within a given time, which is 1 second. So within 1 second, then it means that in 1 second, it means that F must be equal to the number of complete cycles. Okay. So generally, at any other time, F is equal to N over T. Therefore, the SI unit, the derived unit of frequency is 1 on second, which is honored to a good friend, Robert Hertz. So the SI unit becomes Hertz. All right. Period. What is period? Now, Kirsten, help me with period. What is period? Now, okay. Adoma, Charlotte.
I think period is the time it takes a particle to make one complete oscillation.
Come again. The time.
Yes.
Okay. Okay. All right. So just as Charlotte said, period is the time taken to make one complete wave or cycle. The time taken to make a complete cycle. A complete cycle is this. Or a complete cycle is this. Trough to trough or crest to crest. So the time taken to make a wave, a complete wave, which is like this, or a complete wave, which is like this, or a complete wave, which is like this. Any time to make a complete wave whose shape is like this is what we call as a period. Okay, so period is represented by capital T. So capital T is equal to the total time divided by the number of complete cycles. Okay. And so from these two relations, we can establish the fact that, oh, then F relates to period by this equation. If you want to see it, make N the subject from here. N is equal to Ft. Make N the subject from the second equation. T over big T. Then equate both ends. Ft is equal to small t over big T. And you realize that small t will cancel out and F will be equal to 1 over T. So the product of the frequency of a wave and its period, time period, is equal to 1, meaning F times big T is equal to 1. All right. Let's look at the velocity or speed. Okay. Speed. After all, the speed of a wave is the distance through which the wave travels per unit time. Okay. So this definition is carved out from speed equal to distance over time. So the speed of a wave is the distance a wave makes per unit time. Now, in deriving an expression for speed of a wave, we look at for one complete cycle, because if we have it for one complete cycle, we could easily deduce it for a certain number of cycles. So speed v is equal to distance. But what is the distance for one complete cycle? That's the wavelength. The wavelength lambda. The distance for one complete cycle is lambda, divided by the time taken to make one complete cycle, which is the period. So velocity of a wave is actually given by, or speed of a wave is given by wavelength divided by period. Or because F is equal to 1 over T, if F is equal to 1 over T, then V here would be equal to lambda times 1 over T. This is the same as what we have here. And if F is equal to 1 over T, then we can say that this is F. So V, which is the speed of a wave, is given by wavelength times frequency, or V is equal to F lambda. This is how we got this special equation we've been using for waves. You consider the distance covered by a complete cycle or wave, and then the time taken to make this complete cycle. Okay, then knowing this, you can easily derive this. The SI unit of speed is our old friend, meter per second. A question. Let's try a question. Let's apply this in solving a question. And I'm reading. The speed of a radio wave. The speed of a radio wave is 3.0 times 10 to the power 8 meter per second. The speed of a radio wave is 3.0 times 10 to the power 8 meter per second. If a radio station broadcasts on a wavelength of 1,500 meter, what is the frequency of transmission?
On the wavelength.
If a radio station broadcasts on a wavelength of 1,500 meter, what is the frequency of transmission?
Yeah.
Hello.
So please, what's the value for the speed?
It's 3.0 times 10 to the power 8 meter per second.
Thank you, sir.
Welcome.
Mr. Ika, please, can you repeat the question?
Yeah, I don't know. Network, right? Network. The speed of a radio wave is 3.0 times 10 to the power 8 meter per second. If a radio station broadcasts on a wavelength of 1,500 meter, what is the frequency of transmission? Finished? Yaba? Yaba? Yaba is gone. Lizzie? Lizzie is gone. Stephanie?
Yeah.
What have you had? First,
200,000 hits.
come again.
I had 200,000 hits.
200,000 hertz. And I'm glad to say that, in fact, you are wrong, correct. Correct. Okay. Question 2. Question 2. The distance between a crest and its adjacent trough. The distance between a crest and its adjacent trough on a transverse wave is 6.0 centimeter. The distance between a crest and its adjacent trough on a transverse wave is 6.0 centimeter. If 10 cycles of the wave, pass a fixed point in 1 second, if 10 cycles of the wave pass a fixed point in 1 second, calculate the speed of the wave. If 10 cycles of the wave pass a fixed point in 1 second, calculate the speed of the wave. Ekuya Boatma. Ekuya. Ekuya is gone. Network.
Mr.
Hello, Ama.
The
Ama, your line?
distance in centimeters.
Yes, it's in centimeter.
Okay.
Bashas, are you here? Eura is not here. The wave is so huge. The wavelength is long. Are we done?
Yes.
Lizzie?
0.006 meter per second.
0.006 meter per second. Yes. Any different answer? Lizzie is getting 0.006. Yes, go ahead.
0.6.
0.6. Okay, Otniel.
So I had 1.2.
Otniel had 1.2. Stephanie.
This also has 0.6 meters per second.
Okay, let's see who is who. So the distance between a crest and its adjacent trough. Let's do a quick sketch. The distance between a crest, this is a crest, and its adjacent trough. We are told this distance is equal to 1.6. Is it 1.6? 6 centimeters. This is a crest and its adjacent trough. Okay, and we are told that this distance is 6. So if 10 cycles of the wave pass a fixed point in 1 second, calculate the speed of the wave. Speed of a wave is equal to frequency times wavelength. So 10 complete cycles pass within 1 second. It means that the frequency is 10. Because these are the number of cycles passing within 1 second. And that's the frequency. So if frequency is 10 and we need wavelength, what is wavelength? Wavelength is the distance between successive crests or troughs. The distance between successive crests or troughs. So if the distance between a crest and its adjacent trough is 6, then from trough to another crest would also be 6. So that the wavelength, lambda, will be equal to 12 centimeters. What we were given is actually half. So if wavelength is 12, then frequency will be equal to wavelength is this. Then speed will be equal to the frequency 10 times wavelength 12, giving us 120 centimeter per second. Or if we change centimeter to meter by dividing this by 100. So 10 times 12 divided by 100, 2. So we'll have 1.2 meter per second. All right. So if you got 0.6, or in fact, this is the right way to go about. Okay, you must stick to the definition of wavelength. The distance between two successive or consecutive troughs or crests. And then look at whatever you are given and deduce from there. Please, any question? Adma, Charlotte.
Mr. Dia, please, so does it mean that every time, like, the distance should be from crest to crest,
Wavelength.
trough to trough?
Wavelength, especially if you are given a graphical question. Wavelength is the distance between two consecutive or successive crests or troughs. So when you are to determine wavelength, that is how to look at it. All right.
Yes.
Let's look at this particular question whose diagram or drawing is put on the board. After solving this with you, your life will never be the same here. So listen to the question. All right, so the diagram below represents a wave. The whole wave given has a length of 6.0 centimeter. What is the speed of the wave if its frequency is 8.0 hertz? Charlotte, is your hand up?
Sorry, it was the previous one.
So what is the speed of the wave if its frequency is 8.0 hertz? As for this, I expect everybody to get it. What is the speed of the wave if its frequency is 8.0 hertz? As for this, everybody should get it. If you get it, I will take you to Dubai after COVID.
Mr. Dia, please, were you reading a new question?
Yes, this is it.
Can you read the question again?
I've given you the diagram. Now the question is, what is the speed of the wave
Okay.
if its frequency? If its frequency is 8 hertz, what is the speed of the wave if its frequency is 8 hertz? Who is done? I'll go. What have you had?
So I had the speed to be 16 meter per second.
16 meter per. That's correct. That's correct.
No, Mr. Dia, you take him to Dubai.
Yes, after COVID. So
Hey!
you should continue praying that COVID stops anytime soon. So who else had 16? Who else
Mr.
had
Diami.
Who else? More views, more answers. So I take you to Dubai. Oh, Ekwiadoma, Amma, Annalyn, Elvina, Festus, Calvin, Lizzie, Nana, Natalie. Okay. Stephanie. And then Yaba. Stephanie, what did you get? Stephanie, what did you get as your final answer? Yaba,
Please, I'm still on it.
Hey, really? Yaba, what did you also get? Yaba, is she there? So look at it. Speed is still F lambda. F is given 8. I'll need wavelength. Now, what I have is a wave with a certain number of complete. Okay. So you are given the whole length of the wave, 6. So how many complete cycles or waves do we have here? We have 1, 2, 3. So if the whole length of the wave given is 6, and you have 3 complete cycles. Okay, then the wavelength, the length of one complete cycle will be 6 divided by the number of complete cycles, 3. So the wavelength will be 2 meters. If 2, then 8 times 2, 16 meters per second. Okay. All right. Last one. Hey, it's a minute to time. Okay, you'll get it. You'll get it. I'll put them together and then give it to you to think around to see what you can do. So, class, this is where we draw the curtains on today's meeting. I'm sure it's been an exciting day. Or
Yeah.
yes, we're gonna continue tomorrow. We have to go through this with speed, touch on the key areas, and then wash our hands on it. So please, we'll continue tomorrow. Take care of yourselves, and then bye-bye. As usual, your video will be sent. Okay.
Okay.
All right.
Bye.
Bye-bye.
Have a nice day.
The day will be nice. Same you too. Yeah. Okay.